Okay, we're going to get started now. I'm Debbie Liu, Executive Director of eSIG, and I wanted to welcome everyone to our monthly eSIG webinar. For those of you who are not familiar with eSIG, we are a membership-based nonprofit organization. We provide members with objective information, resources, and networking opportunities to support clean energy and energy systems integration decisions. And we do this through workshops, tutorials, webinars like today, through blogs, our working groups for task force activities, and we produce technical resource materials. For those of you who are members, thank you for your support. That makes these webinars and the other work we do possible. So for those of you who missed it, we just got back from the Forecasting and Markets workshop in Nashville, where we talked about large loads, AI applications in forecasting, capacity markets, extreme events, resilience. Our workshops, our monthly webinars, these are open to everyone. So feel free to register anytime on the eSIG website at esig.energy, or you can find us on LinkedIn, YouTube, Facebook, and X. So just a few logistical matters before we get started. We're muting all participant lines for the duration of the webinar. And if you have questions, please go to slido.com, SLIDO.com. Enter in ESIG14, ESIG 14 as the event code. The instructions are also at the bottom of the screen, and you can hit the thumbs up next to questions that you like if you want to vote and help prioritize questions that are submitted. And we're going to save about 10 minutes at the end for questions and answers. And an email with a link will be provided once the video file has been posted, and we'll plan to provide short responses to unanswered questions. So please don't be afraid to ask your questions through Slido. So today we're going down under to hear from our colleagues at the Australian Energy Market Operator, or AEMO, to see how they're managing what's likely the highest penetration of rooftop solar generation in the world. As you may know, South Australia is famous for having more rooftop solar output than demand in some periods. And at the same time, you all know the grid needs more than just energy, and there are a lot of system services that ensure grid reliability. And if the rooftop solar can't provide those services, we need other resources that can. And AEMO is really on the bleeding edge of how to maintain those system services and a stable grid while trying to integrate as much solar generation as possible. So today, you're really lucky. Dr. Jenny Riesz, the manager of operational DER management and an old friend and colleague of mine for many years, is going to discuss their work at AEMO. And Jenny got up super early Australia time, so I think it's like 6 a.m. So we're really excited to have her. She works on analyzing DER performance and behaviors during system disturbances. She develops procedures and processes for operations during minimum system load periods. She develops and validates power system models for DER impacts and operational technologies to manage DERs. So we're super lucky to have her. And with that, Jenny, I'm going to turn it over to you.
Thank you so much, Debbie. Really appreciate the warm introduction. So let me share my screen. Just confirming, has that come up for everybody? Wonderful. Excellent. So thank you so much for the opportunity to be here with you today to share with you a little bit about what we're doing in Australia on managing minimum system demand and high distributed PV, or DPV. So just to start off with, I want to acknowledge that I'm speaking to you today from Australia. There are many different Indigenous peoples. I'm speaking to you today from Brisbane, or Meanjin, as it's also called, which is from the lands of the Yagara and Turrbal people, and pay my respects to elders past, present, and emerging. So a little bit about the Australian Energy Market Operator, for those who aren't familiar with us. We are the system operator and market operator for the electricity markets on the east coast of Australia, the National Electricity Market, or the NEM, and also the WA Wholesale Electricity Market, the WEM. as well as several gas markets. A lot of the talk today will be about the NEM, which has a load of between about 11 to 36 gigawatts. And just to give you a little bit of a sense of scale of how large we are physically, this is showing you Australia overlaid on the United States and Australia overlaid on Europe. You can see, for example, I'll be talking a lot about the South Australian region down here, which I believe is about 40% larger than Texas, just to give you a size of an impression of the physical scale. And renewable contributions are increasing rapidly. This figure is showing you the the proportion of energy in the NEM that's delivered by renewables year on year, as that's been consistently growing. Where we stand at the moment, you can see reaching maximum contributions up around 75% from renewables. And the majority of that is rooftop photovoltaics. A substantial proportion from wind, grid scale solar, but rooftop photovoltaics really are the hero in Australian markets, delivering a really significant contribution of our energy in some periods. Now in some periods, we're delivering more than half of the energy across the whole national electricity market and continuing to grow. So I want to share with you today some of the work that we're doing on integrating distributed energy resources. Importantly, there is a very significant amount of work going on across our whole industry on integration of distributed resources, and I couldn't possibly speak to all of it today. There's a lot of work going on across the regulatory space to look at how we manage changing roles and responsibilities in a high DER system. Also, of course, a lot of work looking out further into the dimensions of planning and the system design to operate in the future. What I want to share with you today is just some little deep dives into a few of the selected elements that we're working on within AEMO's operations division, mostly because of the parts we're working on and the parts that I'm really excited to speak to you about today. So the first area is around the work we're doing on managing low demand conditions, particularly in the next year or two, the sorts of conditions that we are anticipating operating through. So this graphic is showing you how demand has been evolving in the South Australian region, just as an example. So you can see here the peak demand levels that we've been looking at, which are relatively steady. And these are the minimum demand levels, which are steadily tracking downwards. So our first time with minimum happening in the middle of the day rather than the middle of the night was way back in 2013. And you can see here is zero. So we hit the periods some years ago where we hit zero demand on the grid in South Australia, and it's now continuing to track into a steadily negative territory. So that means that South Australia is exporting into the rest of the grid in those periods. And just as another example of what that looks like, it's not actually limited just to South Australia anymore. Certainly that was the initial canary, if you like, in our grid that spent a lot of our initial attention. But really the whole NEM is now tracking to low demand. So this is an example from the Victorian region. And you can see the contribution from rooftop solar in the middle of the day. This is actually an example back from 2023. And you can see what's happening here. The wind generation is being squeezed off. The grid scale solar also squeezed off. The brown coal generation, which is a large component of our generation in Victoria, also getting squeezed in the middle of the day, exporting here to the rest of the grid. And those brown coal units are now being squeezed right down to their minimum levels, minimum operating levels in the middle of the day. And you can see here the maximum contributions from each of the regions of rooftop solar. South Australia, of course, achieving more than 100% of the energy supplied by rooftops alone, as Debbie mentioned, but all of the other states also steadily tracking upwards with more than half of their power supplied by customer rooftops in some periods. So a lot of our focus in operations has been to understand what are the operational risks that will arise in these periods. The initial focus has very much been in South Australia, and we spent a lot of time understanding what we call distributed PV contingency events. And these were particularly important if the South Australian region is operating as an island, which it does periodically. It's weakly interconnected to the rest of the grid at the moment with a single double circuit interconnector that can fail and has on multiple occasions. So this region sometimes does need to operate as an island. And in that case, we need to manage the possibility that a large amount of rooftop PV can shake off in response to a fault or disconnect in response to a fault, which can then contribute to a large contingency event. And I'll talk a little bit more about that in a minute. So the big challenge there was around managing the availability of frequency reserves, particularly fast frequency reserves, given that we would expect to have very low inertia on the grid at these times as well. So very much relying on resources that can deliver very fast frequency response, such as batteries. Around the same time, the West Australia market has also been escalating their efforts around management of PV. And as I showed you before, the WA market is operated entirely as an island. There's no interconnection at all with the East Coast. And so they have their own suite of challenges in having to manage those low demand conditions as an island. Queensland up here can also have to operate as an island. So there's a lot of focus around understanding how that would work, particularly around looking at frequency control. But a lot of the risks emerging here are around simply having enough load to operate the minimum units that we need for essential system services, which includes system strength, voltage management, and frequency control. And if there's not enough load to keep those units online, then we may not be able to maintain all of those services. And a lot of recent focus has been particularly on these issues emerging in Victoria in system normal periods. So we're not looking at interconnector outages anymore, or where the region is operating as an island. In a system normal condition with all interconnectors available, we're now in territory where across the combined Victoria and South Australian area of the grid, we think there's risks that we may not have enough load to support the minimum units that we need to deliver those system services. Now, of course, in planning timeframes, there's a lot of potential to deliver those system services from alternatives. So there's a lot of looking at other alternative sources of system strength and voltage management, such as synchronous condensers, batteries for frequency control, and all sorts of other sources. But those are not available in the operational timeframes that we're looking at. So we're really limited to managing the system with what we have now. And we do foresee periods where we're getting into territory where that's becoming challenging. And the main risk that will emerge here is that if there's not enough load, then we will be violating interconnector limits, and particularly some transient stability export limits from Victoria that we have to manage very carefully. And a lot of the work in this very immediate period right now is around understanding how these issues could emerge across the whole NEM market altogether, just not having enough load to maintain enough units online across the NEM, and leading then to insufficient system services and potentially operating insecure if we can't maintain those system services online. So my team's doing a lot of analysis to understand the sorts of conditions where that might arise, to build the procedures for our control room to be able to handle that in an orderly way, and to have the displays and tools that they need to see those periods arising and make efficient decisions around them. To manage these periods, we've introduced what we're calling our minimum system load framework, which is modeled after our framework used in high demand periods, the lack of reserve framework, or LOR framework. So the LOR framework is about ensuring there's sufficient generation, and it looks at the potential loss of the two largest sources of electricity to understand as we're approaching system security issues. The MSL framework is the mirror of that, about ensuring that we have sufficient demand, and it manages the potential loss of the two largest loads, which could include an interconnector. So this framework gives a structured way of providing notices to the industry and helping to clear those levels. So MSL1 is the level of demand where we're two credible contingencies away from MSL3. At that level, we would publish a market notice as an information for the industry. MSL2 is the level of regional demand where we're one credible load contingency away from MSL3. And at that point, we start to take actions to make sure that if that contingency happened, we would remain satisfactory, which means that everything is still within limits. and we could re-secure, so get back to a point of being one further contingency away within 30 minutes. And MSL3 is the level where we need to increase demand to maintain system security. So we would see some sort of violation at that level. And at this level, we'll direct our network service providers, or NSPs, to maintain demand above that threshold. So just to speak to the range of possible actions that would be taken, this graphic here is illustrating, just illustratively, by number of days of the year, the load range that we might be in. Of course, most of the time we're in this normal range of demand, and we hope very much that market mechanisms are driving customer response in those periods and sufficiently managing the supply-demand balance in those periods. And there's an awful lot of work happening across AEMO and the industry around making sure that we've got sufficient mechanisms in place. There's a lot of further work required to make sure that customers have appropriate access to the market and can participate effectively in those normal periods. But even with those measures coming online, we still expect that there will be periods, rare periods, but periods that will occur that will be outside of that, when we need to have tools in place to be able to manage those extreme periods. So there's a hierarchy of actions that we'll work through if we're getting into approaching MSL periods, such as running the network to temporary limits, recalling network outages if necessary, potentially directing units. And the very last mechanism that we might use, we're calling the emergency backstop mechanism, to manage very extreme minimum system load periods where there is a system security issue arising. And it's very much for very rare periods where there's simply not enough demand to maintain system security. So that includes all sorts of things, containing larger embedded generation in the distribution network, active curtailment of distributed PV. There's a whole lot of mechanisms starting to come online to make that available. Shifting of things like customer hot water systems or other controllable loads. There's also some more extreme measures that would be on that list if we exhaust the ability to move load or actively curtail customer distributed PV. We could get into mechanisms like enhanced voltage management. That's a mechanism that's we've brought online in some regions to be able to slightly push up the distribution network voltages to deliberately curtail or trip customer PV systems, which obviously is not a preferred method, but has been very effective on several occasions as a last resort for maintaining system security. And the very last mechanism available to increase demand, if necessary, is to shed whole reverse flowing feeders in the distribution network, which can effectively increase demand, but obviously has an extremely high customer impact because it's shedding all of the customer load on the feeder as well. So that has not been used in an incident, a power system event yet, but is a mechanism that we want to have online as a last resort. And all of these mechanisms we really treat in our procedures as being the mirror of load shedding in high demand periods, which is a very important tool to have available to manage a lack of reserve condition if we simply don't have enough don't have enough generation to supply the demand. Of course, we don't want to use load shedding, but it is important that that tool is available if necessary to keep the system in a secure state. So to give you a little bit of a day in the life run through of what these procedures might look like if we hit these low demand conditions. This is illustrating just an example from the Victorian region. You can see here for this particular day what the MSL 1, 2 and 3 thresholds might look like for that day, and they do vary depending on the system conditions such as the units online, the network conditions and so on. And here's our forecast demand in the purple. And you can see it's tracking well down below those levels on this illustrative day. So our controllers would be looking at this forecast and issue a market notice at the start of the day, indicating that we're forecasting that we're falling below the MSL1 threshold. As the time approaches, they'll be taking all the actions that they can to clear the MSL 2 and 3 conditions, releasing a market notice to market participants so they're aware, liaising with our transmission providers, if necessary, recalling any planned outages that are reducing the region's export capability, constraining off significant non-scheduled generation, so large distribution connected generators that can be curtailed. And if there's any larger units that are still online for some reason, if they're not required for system security, constraining those off as well. So they'll work through a hierarchy of actions to try and clear the MSL2 and MSL3 condition. Some of those actions will change the threshold, some of them will change the demand. We also are using batteries as a type of reserve. So batteries can, of course, act as a load to help remove the trough periods. And some batteries may well be used for that in the future. The way that we're using batteries at the moment is as a reserve. If we do fall below the MSL2 condition, the batteries will sit close to empty at their minimum state of charge, ready to ramp up as a load if need be, because it takes about 90 minutes to activate active PV curtailment. And as I mentioned earlier, there's an obligation to return to secure or use best endeavors to return to secure within 30 minutes. So we cannot bring online that active PV curtailment quickly enough to achieve that. So we use the batteries as a stopgap measure to ramp up as a load very quickly and buy us time to return to secure by bringing online that active PV management if that contingency occurs. So we'll discharge the batteries in the early part of the day and then hold them at their minimum state of charge ready as a reserve through the middle part of the day. 90 minutes before the MSL3 condition will then instruct the network providers to maintain demand above the necessary threshold. And then they will maintain that through the middle part of the day, and we cancel the MSL condition at the end of the day as demand rises back up again. So there's a lot of complexities in this, especially if we're looking at multiple regions having these challenges all at the same time and how actions get shared across multiple regions. And we're working through a lot of that with all of the stakeholders involved at the moment. If you're interested in understanding more about this, we released a report in November last year that called for the need for urgent measures to implement these emergency backstop capabilities in all of the NEM mainland regions, referring to the measures to be able to reduce aggregate distributed PV generation if required when all other options have been exhausted. You can appreciate that's a very sensitive topic for customers because we're talking about curtailing mums and dads' rooftop systems. And of course, customers have invested in those systems with the intention of supplying their electricity. So very, very important to make sure we're working with the entire industry around implementation of those measures. That's been very involved, very complicated, an enormous amount of work invested by the distribution network providers, the original equipment manufacturers, a lot of engagement with installers and customers and so on to implement those measures. This is one of the graphics from the report that I just mentioned that's showing you the levels of minimum operational demand that we've achieved historically and then how minimum demand is projected to move forward in the future. This is the amount of demand that's being met by distributed PV in these scenarios, which you can see has already exceeded half. And we're projecting to extend into levels of 80–90% of demand on the grid being supplied by mums and dads' rooftop systems in the very near future. These levels here are indicating the thresholds where we think under some circumstances, we may need to use emergency backstop mechanisms if we had a particular combination of outages, for example, and even in the best case system normal. And we're projecting falling below those thresholds in the very near future. These bars indicate the amount of emergency backstop capability that we are projecting to have based on current measures in a worst case and best case in the A/B scenarios there. So you can see with demand continuing to fall, a really urgent need to bring online more of that capability. And the different bars are indicating the different types of capability that we think we'll have available. So it's a bit of a race against time to bring those measures online. And it is hard to overstate exactly how difficult it is to bring online very complex measures to be able to manage thousands and thousands of rooftop PV systems simultaneously in an operational manner. So a lot of work happening at the moment across the industry to bring those capabilities online. So I want to dig a little bit further into the challenge around PV contingencies that I mentioned earlier. So this is something that was flagged quite a while ago in the NEM. This is an early event that happened in 2017, where we had a series of faults in the middle of the metropolitan area in South Australia. You can see here, these are the minimum voltages that were measured on the network, right in the middle of the South Australian region. And these are our estimates of how much PV looks like it disconnected or was shaken off by those faults. And you can see in the immediate vicinity, which is right in the middle of where all of the PV is installed, around half of the PV we estimate was shaken off, and continuing out even to the extent of most of South Australia still seeing about 20% of PV systems shaken off. So there's a lot of effort around making sure that we can collect the data sets to have visibility of this kind of shake-off. That does require that we can see individual PV systems, at least a sufficient sample across the grid to be able to understand if they are disconnecting, and we're seeing this sorts of behaviour. And we've observed this now across very consistently across many, many, many power system incidents. To give you a little bit of a history of how this has evolved, we started back in 2017, 2018 to observe these incidents and started talking about this as part of our incident reporting, where we were observing these shake-off events. And we compiled this into a report around 2019, talking about all of the combined evidence that rooftop PV was shaking off in power system events. That then was a really important reference to feed into processes with Standards Australia, who published the Australian standard 4777, and they worked over this period to improve that standard so that it would have improved ride-through requirements for distributed PV. That standard was published in late 2020 with those improved requirements, and then became mandatory 12 months later. There was a grace period of 12 months to allow the equipment manufacturers to adopt and test to those new standards. And in the intervening period there, we brought together a more comprehensive capstone report that brought together a more comprehensive view of everything we'd seen around DER behaviours over the previous 5 years or so. Even though that standard came online and then became mandatory, we were observing power system incidents through 2022 and 2023 and still observing considerable shake-off, even from new installations that we knew had been installed since that standard became mandatory. So we started collecting data around compliance with that new standard. The original equipment manufacturers here were really critical in being able to supply to us data around the standards and settings that were being put onto their devices. And we discovered that from a whole range of data sets that compliance was less than 50%, and in some cases well less than 50% of inverters being set properly to that new standard. So we reported on that as well, and then used that as a basis for working with industry around improving compliance. A very substantial amount of work, particularly from the original equipment manufacturers, then meant that by late 2023, we could report that compliance looked like it had significantly improved, which was a really big win for the industry. And we now believe that is holding from the data sets that we can see that we are seeing compliance with that standard. And when we test in the laboratory conditions that standard, it looks like inverters do ride through successfully. So very much a good news story around being able to make those changes with industry and a lot of work from a lot of different parties. But what I want to emphasize here is the timeline for rectifying these issues. This was first noticed around 2017, 2018, and it's really only around 2024, 2025 that I would suggest we've actually got measures in place that are addressing that successfully, and now seeing growing levels of inverters connected that will ride through. So for these sorts of issues where we're dealing with distributed resources and customer devices that are very distributed across the grid, we need to allow for really long lead times to address these issues. They're very involved processes. Just to share with you a little bit more about the analysis sitting behind that. So this is the data that we've collected of new installations that were since 2022, when they should have been installed according to that 2020 grid code. And you can see back in early 2022, we were seeing only around 40% of the inverters being installed correctly to that new standard. Most of them were being installed still on the old standard. So there was a lot of need for change management processes working with installers and industry around introducing those new standards. But since we worked with the original equipment manufacturers and installers, steadily seeing those rates climb, and we now believe we're achieving over 90% compliance with those new standards. This is just showing you that the different actions that were taken by the different original equipment manufacturers. There was a whole suite of actions that they took when we raised this with them to ask what they might be able to do to help improve compliance. The original equipment manufacturers have an enormous amount of influence over compliance by the way that they design their products and particularly the way they're designing their menus and the way that they interact with installers who are commissioning these new systems. So these are showing for particular manufacturers the compliance rates we saw from their systems in early 22, early 23, and in early 24 is the third bar there. And you can see some of them, many of them saw really immediate improvements when they did things like just removing those old legacy grid codes from the menus that were offered to installers. Others have done things like setting the default as the new grid code or marking legacy codes as obsolete or various other updates. Certainly the most successful approach has been simply to remove them, but some of these other methods also look like they've been quite successful as well. So it's a real lesson here around if you're introducing changes to standards, it's very important to think through how that all interacts with folks such as the installers who are out on the front face of introducing these new changes and making sure that it's as easy as possible for those to be implemented. It's worth noting here the challenges around visibility. The data sets that we're working with to try and do these assessments are quite difficult to work with and incomplete. So thinking about the data that is provided from these processes is quite important. This is showing you our estimates of the amount of data that is visible to the original equipment manufacturers, who are our main source of these data on compliance. They can only see around 60% or 60 to 65% of their inverters. Many of them are now able to provide quite large samples to us to look at to estimate compliance rates. Some are only able to provide small samples. A large proportion are simply not visible, largely because the devices are just not connected to the internet. So we have no idea what standards are set on those devices. But this is improving all the time. Data quality is improving, particularly as more and more of these devices are becoming internet connected now. So the ability to extract these data sets is improving rapidly. But still a lot of challenges around exactly how that data is being collected, how it should be shared, and a lot of issues that we're working through as an industry around how that should look going forward as these data sets become more and more important for understanding how the power system will behave in these low demand conditions. There's also a whole suite of issues that we're still grappling with. So this chart here is showing you these are all different power system incidents that have happened on different dates and different parts of our grid, and showing you the proportion of distributed PV that disconnected in those events. The purple bars here are the small systems, the less than 30 kilowatt rooftop PV systems, and the green bars are the larger ones in the range of 30 to 100 kilowatts. You can see some of these have quite large error bars because they're relatively smaller sample size in that larger category. But the really important thing to note is that these disconnection proportions are really large and much larger than what we're seeing from the small rooftop systems. So we're still investigating what exactly is going on there to drive these really high proportions of systems disconnecting. At the moment, the amount of capacity in that size grouping is relatively smaller, so this doesn't constitute a system security issue on its own at the moment, but certainly something that we would like to rectify before that becomes larger, and it is a growing category. Our best guess at the moment is that this might be related to some form of central protection on site that's much more sensitive to disturbances, but it's been quite difficult to investigate again because the data is actually quite difficult to collect to observe these behaviours and understand and diagnose what's going on. This chart here is giving you an indication of our best estimate of what we think will ride through in faults on the grid, looking at all systems that installed up to a size of 5 megawatts across the whole NEM. So this is when the new standard became mandatory, the 2020 Australian standard with the new ride-through requirements. And you can see from that point onwards a growing proportion of systems being installed in the green. And this is installed capacity across the whole NEM. So we're tracking upwards of 20, 30 gigawatts of rooftop PV across the NEM. And this growing proportion that we do believe for ride-through. These are our older systems on the 2005 and 2015 standards that we believe will have very poor ride-through capabilities. And in the middle here, those ones I was just showing you with the larger systems that we think have very poor ride-through capabilities. But with all of these measures, we think we have achieved essentially a plateauing of the amount of capacity being installed that has poor ride-through capabilities. So very much we believe from the power system modeling that we've been doing that we really nipped this in the bud just in a nick of time. Distributed PV contingencies remain a concern in South Australia, particularly if we're operating that grid as an island. As I mentioned earlier, particularly with the low inertia in the island, frequency management with these sorts of contingencies can be quite a significant challenge to manage. But we're very much hoping that we've nipped this in the bud in just a nick of time so that frequency management and these contingencies will not become a significant problem in the rest of the grid. They'll remain smaller than the largest credible contingency that we're managing from other sources. So yeah, really positive outcome for the industry. A note about incident analysis. This has been a really significant part of our work, just to be able to understand what distributed PV systems are doing in disturbances. I wanted to share with you a little bit about a particular incident recently that the incident report has just been published. So if you're interested, definitely have a look. This is quite a significant event on the 13th of February, 2024, where we had 6 towers on the 500 kV network failed due to convective downburst winds that exceeded the rating of the towers, and that resulted in the fault and subsequent trip of those lines. And of particular interest to us in dealing with distributed PV and load behaviours, we saw some very low voltages recorded in the Victorian transmission network, down below 0.2 per unit. And this is the measurements of total regional demand for the total Victorian region. You can see a very significant drop in demand. We lost almost 1 gigawatt of load that we believe disconnected. And this is probably the most significant loss of generalized load that we've seen. So a lot of our efforts are in understanding shake-off of distributed PV, but we also need to understand the shake-off of load that occurs in these same events so that we can then model how the two of those interact in these power system events. And load shake-off is considerable in the sorts of events that we're looking at. This is showing you again the distributed PV disconnection rates. For the smaller systems, a moderate amount of PV disconnected from the older systems. These are the newer systems, which you can see have improved in their behaviours with the new 2020 standard becoming in and improving compliance with that. These are the larger systems, which I flagged before. We're consistently seeing those higher disconnection rates from them. So a lot of work to understand all of this so that it can feed into our power system models and represent these behaviours accurately. One of the most interesting elements of this event was looking at the subsequent operation after that event. It actually, due to the transmission damage on the 13th of February, the South Australian region was operating at credible risk of separation for a few days until the 15th of February. And as I mentioned, we've become concerned about management of distributed PV contingency events when South Australia is operating as an island or at credible risk of separation from the rest of the grid. And we had a distributed PV3 condition arise on the 15th of February. So that means we were forecasting violations of interconnector limits. And the only action we had available to us, because we couldn't bring the line back to service in time, was to maintain system security, was to reduce the distributed PV generation in South Australia. So you can see here, this is the forecast of PV generation, and then the period where we requested that was reduced, which it was. Here's the threshold of demand that we asked the networks to maintain, and the actual demand that they were able to track in purple there. So it was a relatively small amount of curtailment, but required to keep us within the secure range. So the actions that were taken there was to curtail about 50 megawatts of PV. Most of that was larger systems that were curtailed through SCADA control, but there was 5 megawatts of small-scale distributed PV that was curtailed through the new CSIP Oz standard, the Common Smart Inverter Profile Australia, under the Smarter Homes framework. So 5 megawatts is a drop in the bucket in terms of system security, but this was particularly important because it was the first observation of the use of these systems using this new protocol to manage for active PV management. So we've done a lot of analysis around exactly how that worked. What did we see? How did it perform? To really help us unpick where it needs improvement. So a lot of work with SA Power Networks to understand exactly how these systems performed. We estimate that there was about 16 megawatts of installed capacity that was on the flexible export limits mechanism, which is how these systems were activated. And based on our analysis of smart meter data, we believe that 16 megawatts was generating a total of about 11 megawatts in these periods. About 2.2 megawatts of that was self-consuming at the customer site. The remaining 8.9 megawatts exported into the grid. And we believe about 5 megawatts of curtailment was successfully achieved during this period to bring demand up from about 11 megawatts back up to the 6 megawatt mark or so in that event. There's a whole bunch of systems here that did not respond. So that was due to a whole range of reasons. There were some systems that had not yet passed the capability testing process, which is the onboarding process that tests and confirms those systems are indeed set up correctly to deliver this curtailment process. And SA Power Networks has continued work with them to reduce that number down. There's also a bunch of sites which had passed the capability test but didn't respond on the day. And SAPN is also working with the original equipment manufacturers and others to try and reduce that capacity as well. There was also a bunch of systems which had chosen a fixed export limit. So they chose not to be responsive, but should have been limited to a 1.5 kilowatt export limit and were non-compliant with that limit. So SA Power Networks has also introduced processes to improve compliance with those limits. So a whole suite of reasons why systems might not be responding and a whole suite of actions and collaboration with stakeholders required. SA Power Networks has been doing a phenomenal amount of work to bring this capability online, and it's improving all the time. So big lessons here around, again, this very significant amount of effort that's required if we want to bring online new capabilities to manage active distributed PV. If we want to manage distributed PV actively, we really must anticipate that there's a long lead time for those mechanisms to work successfully and a huge amount of engagement required with a very broad range of stakeholders. So you must allow significant lead time to bring these mechanisms online at operational scale. And full credit to SA Power Networks for really excellent engagement and really driving this forward in the Australian system. So a lot of this power system incident analysis is very important to understand how PV and load will behave so that we can then reflect that in our power system models and make sure that that's then reflected in all of our assessment of power system limits. So this figure here is showing you, as I mentioned, minimum power system demand, and just emphasizing again, the amount of demand that is being met by distributed PV at the moment is truly phenomenal. And so if you're not modeling that distributed PV accurately and the load that sits behind it, you're essentially missing at more than half of the power system that does have complex dynamic behaviors that need to be recognized in dynamic studies. So just to give you a little bit of a track of the work that's been going on, developing these models has been very non-trivial. So a lot of the work around understanding behaviors has fed into this. We developed our first prototype models back in 2019, a lot of work to understand the parameters to go into those models for load as well as PV based off of our observations of PV behaviors. Our first models in PSSC were released in 2022, and we've since released a couple of updates to those and models in PSCAD. And those models are now being applied by AEMO and also our network providers to calculate updated security limits. And these models are having a substantial impact on security limits in many different ways. The old models that we had for load and PV were a very simple static model. We've now moved to a full dynamic model and certainly have not been reinventing the wheel here. Full credit to folks at WEC and others who've been developing the basis of these simplified models for distributed PV and load. We've absolutely been adopting the composite load model and distributed PV models from those efforts. The distributed PV model itself has many different elements: reactive power controls, active power controls such as over frequency droop, which is an element of the Australian standards, and the tripping logic, including over and under voltage in a linear manner, 13-stage over and under frequency protection, and rock-off protection as well. And a lot of that we've been tweaking to try and represent the shake-off behaviors that we've observed. This is a figure showing you for all these different disturbances we've observed on the grid in different regions, the amount of shake-off that was observed in that event in the dots with the error bars, and then the performance of our models in the solid bars. These are nighttime events that we're for tuning our load model, and these ones daytime events where we can see the PV model behavior as well as the load model behavior. And you can see that although there's significant error margins, we estimate an error margin of around 20 to 30% on contingency sizes, the models are doing not too badly in terms of representing those shake-off levels from both the PV and load. So an enormous amount of effort from the team around calibrating those parameters and getting it to represent those shake-off behaviors. A lot of the recent focus has been around validating the transient behaviors of the models as well. So for this, we've been doing single load infinite bus studies, where we essentially play back the voltage and frequency that was measured at a particular bus in the network at a radial location, and then aim to replicate the active and reactive power responses that were measured at that location. It's worth emphasizing again the challenges we've had around data to actually be collecting this kind of high-speed data, at least 20 millisecond resolution from radial locations that have a substantial amount of PV in the network, is something where we're flagging a need for uplift for more data from those locations. But you can see here the performance of our models. The data that was collected is in the black, and the old model is in the red, the exponential model, the new model's in the blue. So you can see arguably the new model's doing a somewhat better job of representing recovery rates after the fault, for example, doing a significantly better job of the transient behaviors of reactive power here, tracking much better against the data compared to the older models. And this is showing over a longer time frame here, measuring that shake-off behavior. Certainly the models are not perfect. We still see a mismatch, but doing substantially better than the older models did. So a lot of further work that we want to do to improve these, but certainly they're much better than the models we had before. One of the behaviors coming out of these models has been significant swings in demand that we're seeing post-fault. This first came up when we were using the models to study inertia requirements in the grid, and we noted that there was this very brief transient increase in load immediately post-fault, which is due to the composite load model recovering slightly faster than the PV model post-contingency. And that behavior is under investigation as to understand what exactly is going on there. The recent event that we saw in March 2024 has been particularly instructive in understanding this. So this was a series of current transformer failures in South Australia. You can see here the minimum voltages that were recorded across the Adelaide region in South Australia. And when we look at data from this event, again, we can see here these very large swings actually occurring in the data. So here is the large rise in demand happening post-event, and you can see our model in the purple there is representing that quite well. So again, a really good validation of our model behaviors. And really significantly, it does validate these operational demand swings that we're seeing. So we do believe this is probably a real representation, with these swings post-fault being a real representation. And this figure here is showing you how that swing is more significant in places where we have more distributed PV. We can see that the swing is larger, which is, again, strong validation that it does appear to be a real behavior that we're really seeing on our grid. When we project this forward in simulation outcomes, this is showing that it can lead potentially to very large swings across the interconnector in that transient time frame, and that potentially could have significant impacts on transient limits, for example. So we're still in the process of really understanding exactly what that means and continuing further investigation, but it looks like a very interesting behavior that we want to investigate further. The very final thing I'll mention is that we're also launching a very major program around uplift of our operational systems. And this is all very fledgling at the moment, but recognizing we need a fairly substantial uplift of all sorts of areas of our operational systems to be able to handle distributed resources. We're doing a significant mapping of all of our operational systems at the moment to then identify which are most impacted and prioritize those for uplift, and launching some major uplifts of some immediate focus areas, which includes things like control room tools, tools for calculating these MSL thresholds, our incident analysis tools, automating a lot of the management of these big data sets we're now using, making sure distributed PV is integrated into our energy management system at the right locations, and integrating these models that we've built into our modeling platform so that they're robust and easy to use. So a lot of exciting work really launching around all of that as well. And if you'd like more information about everything I've talked about today, head to this website, just search for AEMO and Distributed Energy Resources and Operations, and you'll find there reports that cover pretty much everything that I've spoken about today. So thank you for your time, and back to you, Debbie.
Thank you so much, Jenny. That was a fascinating discussion of everything distributed solar going on in Australia. I'm going to take the moderator's prerogative and ask the first question, which is around lining up demand with your solar resource. And I wanted to know, what is it that the industry in Australia is doing to maybe statically get more demand into the middle of the day, like with time of use rates, for example, or maybe dynamically get more load into the middle of the day, maybe through a DER program, or maybe through some kind of, dynamic, maybe day ahead or real-time rates.
Yeah, absolutely. And this gets more into the realm of, with everyday operation, how do we drive those behaviors and encourage customers to move load into the middle of the day? So all of the options that you mentioned, of course, are on the table around offering customers different tariffs, moving controllable loads such as hot water, making sure that we've got incentives for new types of controllable load, such as electric vehicles coming online. The main initiative that we're looking at, or one of the big initiatives, is called Integrating Price Responsive Resources, IPRR, which is a very major reform program that's looking at how we make sure that there's easy pathways for customers to participate in the scheduling process and have access to or some visibility of wholesale market prices, and for us to have some data as well about how they're planning to operate their loads and active customer resources. So that's in the phase at the moment, working through a regulatory reform process and how we update the rules and bring that into reality. But yeah, a lot going on in that space.
Oh, that's fantastic. Once you guys get that implemented, we'll have to have you come and talk about that and how it works. Okay, so Rick O'Connell has a question. He wanted to know, can you help us understand why it takes 90 minutes to curtail the rooftop solar?
Yeah, so there's a whole sequence of events that has to happen. The first is that there's a little bit of time that it takes just to assess what's going on the grid. So we need to allow roughly 15 minutes or so for the control room to be able to collect together all of the data, and understand probably a very complex scenario that's going on in that day with lots of other factors, and then pass instructions down to the transmission provider, then to the distribution provider. But that whole sequence is fairly similar to what we might be managing on a high demand day, for example. The bigger challenge is that it's actually just very complicated if you want to then send out signals to a very large number of customer rooftop systems. Those signals have to go through the distribution network servers that they're using to handle active PV, and then a lot of them is going to the original equipment manufacturers, who then also have servers that are managing curtailment of their PV. And we're seeing that there's lots of reasons that delays can happen. So for some of those original equipment manufacturers, they need quite sophisticated capabilities and quite sophisticated servers that can handle very large loading if they're going to be curtailing and sending out signals to a large number of customer PV systems. And they need to be designed with that very high level of loading in mind. So we're seeing examples where there are delays. due to those systems and working with those equipment manufacturers around improvements. But it's very much an active area of consultation around what's causing those delays and how do we speed that up.
Mhm. There's another question about whether there's a price signal in the AEMO system for PV customers to reduce their active power output and increase or maintain reactive power consumption during one of these minimum system load events.
The main signal from AEMO is the release of the market notices. So as I mentioned, the first signal will be the MSL1 market notice, which is really just a notice to market to say we're entering into these conditions and essentially seeking a response from market. If you have the ability to scale generation or to increase load, this is the time to do so. So it's not so much a price signal. The prices should already be very low in these periods. So we anticipate prices at floor or very low in these types of minimum system load periods. So that would be around negative $1,000. And we're seeing that customers or market participants are wanting to continue generating through those periods. They might have very high cost to decommit their unit and so want to operate through those negative price periods.
Sure. I think another part of this question was around reactive power consumption. If there was anything that you do to have maybe some kind of active voltage regulation or on the rooftop solar.
Most of that's managed by the distributors themselves. It's really their responsibility to manage the voltage and reactive power contributions on their network. I don't believe that they would be seeking a response actively from the rooftop PV itself, but more using the standards that define how they should be responding, such as volt var, volt watt responses, and then actively managing through their distribution equipment.
Sure. Thanks. Mark O'Malley asks, you mentioned system strength as a service. I consider a service something that can be measured and rewarded. So is it really a service?
That's a deep question that I'm probably not the best place to answer.
Yeah.
But
Yeah.
I acknowledge it's a great question.
Right. We could have a panel session on that someday. Davis Ray from SRP asks, when increasing voltage on the feeders to force the rooftop solar to trip, how much of an increase of voltage is needed? And have there been any negative impacts from this strategy?
So it's got to be just enough that it's starting to trigger things like the volt watt response on inverters or the trip settings. The levels are quite small, so it will of course vary along the length of a feeder. The voltage can be quite different at the top versus the bottom of a feeder. So there was a lot of work done by the distributors in introducing those mechanisms to use data such as the data collected from smart meters to understand the full extent of how voltages were moving around their network, making sure that that's within ranges that are considered safe, and also monitoring the impacts on customers and customer equipment, because of course we want to be very careful that we're not pushing volts into the range that could be damaging for customer equipment. So the distributors would be better placed to share all of that data, and happy, you should probably invite them to do a presentation around that. But the ranges are small and were tested very carefully through their trial process.
Okay, great, thanks. So Rick O'Connell is asking about load management, which we sort of just discussed. Fernando Cotton from ONS is asking, how do you share the curtailment among central versus distributed PV?
The general approach is that we will work to manage market participants first, so the larger systems, and do whatever is feasible to be moving around larger systems. So, and that will depend on the capabilities of those units as well. So they will have different limitations that need to be managed, different minimum loading levels they need to achieve, and different challenges if we're asking them to decommit. But the general approach is that we will work with the larger systems first to within their capabilities before we would start working with any sort of rooftop systems.
Mm-hmm. Okay. Let's see. Then we've got some questions around synchronous condensers. I don't know if you want to go into this about how large synchronous condensers helped with system strength and inertia?
Again, there's probably others at AEMO that would be better placed to speak to the system strength frameworks. Obviously, a great deal that's been going on there, but definitely worth saying that the very large synchronous condensers that have been installed in the South Australian network have been absolutely crucial in terms of allowing operation with fewer of the large synchronous units online. And that then, of course, intersects with these minimum system load periods where we want to be operating down with very few units. So they've been a very important contributor to that system.
Okay. There's a question on fast frequency response. I think that also might be, but if you're interested in answering, Davis Ray is asking what types of FFR devices are favored by AEMO and are IBRs successfully used to satisfy these needs?
Absolutely. I mean, the IBRs are very, very capable in that dimension. So we are neutral about technology, definitely seeking more of that fast frequency response. There was a new frequency market introduced recently, a very fast frequency response, which is seeking response within 1 second. So we're still in the stages of that really ramping up and coming to fruition on the grid, but that's really aiming to elicit a response from all of the IBRs. The batteries, of course, are extremely capable in this dimension and becoming, again, a very important contributor to maintaining all of the different system services that we need.
Great, thanks. I realize we're hitting the top of the hour, so we're going to need to wrap up. Jenny, I want to thank you for your presentation today. For the audience, as I mentioned earlier, an email is going to go out once we post the video file. We will answer the questions we didn't get to and post those as quickly as possible. And we really appreciate everyone's engagement. We look forward to seeing you soon. We're going to have a July 22nd I2X webinar meeting on interconnection standards. We have a July 23rd joint webinar with GPST on DER flexibility. And again, all the information about our webinars and meetings can be found at esig.energy under events. Everyone's invited. And Jenny, thank you once again. That was a fascinating and information-packed presentation. I'm sure a lot of people are going to be reviewing the video file on this again. We look forward to seeing everyone again in the near future. Thanks so much.
Thank you so much.